Welcome to lecture number 23 of my series on classical thermodynamics. This is part 2 of stability considerations in thermodynamics. Let me remind you that in the last lecture, we saw that for a thermodynamic system to be stable, the entropy must be a concave function of its arguments. So entropy, S, with the arguments u plus delta u and v plus delta v, added to S with arguments u minus delta u and v minus delta v, must be less than or equal to twice S at u, v, m staying constant throughout the process. Now this ensures that a small fluctuation in energy from one region or a volume from one region of a system in favor of another region does not lead to an increase in entropy and consequently a spontaneous change. So such spontaneous inhomogeneity development would be prevented as long as this condition is valid. So this is the concavity condition which entropy has to satisfy. And locally, that is for small delta u and small delta v, this condition translates to the following. Del 2s del u2 is less than or equal to 0, and the product del 2s del u2 times del 2s del v2 has to be bigger than the square of del 2s del u del v. Now, while we did not mention del 2s del v2 less than or equal to 0 separately here, it should be easy enough to figure out that the first two conditions that we have written down actually also implies del 2s del v2 is less than or equal to 0. It just isn't an independent condition to worry about. Now, just as S expressed as a function of u, v, n has complete thermodynamic information about the system, a more common version is actually U, the internal energy, expressed as a function of SVN. And the second law, expressed in terms of U, essentially becomes that if entropy, volume, and number of or amount of particles is kept fixed in a composite system, U takes the minimum possible value consistent with the constraints that are acting on the system. This helps us to rewrite the stability conditions in terms of U, and essentially is just the opposite of the stability condition for entropy. Whereas entropy needs to be a concave function of its arguments, U has to be a convex function. So U at S plus delta S, V plus delta V n added to U at S minus delta S, V minus delta V n is actually greater than or equal to, as opposed to less than or equal to as was the case for entropy, twice U at SVN. So a local version of this equation, that is the version you get when delta S and delta V are tiny, in fact in the limit as delta S and delta V go to 0, are the following. Del 2U del S2 is greater than or equal to 0. Del 2U del V2 is greater than or equal to 0. And these two things are actually the same as del T del S and minus del P del V respectively. And also, of course, you have this mixed condition del 2U del S2 del 2U del V2 minus del 2U del S del V whole square is greater than or equal to 0. Note that the del 2U del S2 greater than or equal to 0 condition actually can also be written in the form T del T del S, T del S del T at constant V and N, these are actually derivatives at constant V and N, greater than or equal to 0, which actually of course means CV is greater than or equal to 0. This is an expression of physical significance. We will see more physical results which follow from the stability conditions in what is to come today. Now that we have seen the result for internal energy expressed as a function of SVN, it's natural to ask what would such conditions imply for the other thermodynamic potentials like enthalpy, Helmholtz free energy or Gibbs free energy? Let me remind you that you get the other thermodynamic potentials starting from U as Vn by carrying out something called a Legendre transformation, which allows you to swap one variable in favor of the derivative of the function with respect to that variable without losing any information. To understand the connection between convexivity or concavity of the thermodynamic potentials, let us first look at what happens when you do a Legendre transformation of a function of a single variable. So let's say we start with a function of a single variable, f of x, and Legendre transform it to g of p, where p is nothing but df dx. Now we know that the Legendre transform g of p is given by fx minus the product of p times x. Now, from this it immediately follows that dg, the differential of g, is df minus d of px, and df is of course p times dx. When we subtract p dx plus x dp, the d of p times x, from that get minus x dp. And therefore, x, the original variable, is actually minus dg dp. Now from this, what follows is the following. The derivative of x with respect to p, which of course is the second derivative with a minus sign of g with respect to p, from elementary calculus is a reciprocal of dp dx, and dp dx, p being df dx, this expression is nothing but 1 over d2f dx2. So what this tells you is that d2g dp2, the second derivative of g with respect to its argument, and d2f dx2, the second derivative of the original function f with respect to its argument, are connected by this relation. One is the negative of the reciprocal of the other. What is of extreme importance for us is that these two second derivatives have opposite signs. That is to say, d2g dp2 has the opposite sign as d2f dx2. And that immediately implies that if f is a concave function of x, g has to be a convex function of p. So the concavity or the convexivity of the function reverses under a Legendre transform. Now, the only difference between this case and the case that we see in thermodynamics is that in thermodynamics, we have functions of multiple variables, and we usually do Legendre transformations on one variable at a time. Now, once that is done, the same conclusions actually work for multiple variable functions as well, except that this reversal of nature between concavity and convexity, of course, happens in the case of the variable that is being swapped out, the one on which the Legendre transformation is being done. So, starting from the fact that u is a convex function of S, V and N, we can easily figure out what exactly will be the nature of the second derivatives of the other thermodynamic potentials with respect to their arguments. Now, before we go any further, let me also stress that the second derivative condition, this is something we have already seen in the last lecture, is not really as restrictive as the concavity or the convexity condition. This works only when the change in the arguments is infinitesimally small. For large changes, it might so turn out that even if the sign of the second derivatives is not what you expect it to be, you might still have concavity or convexity. Having said that, let us focus on the local versions, that is the second derivative versions, for the time being. The enthalpy H can be obtained from the internal energy U by doing a Legendre transformation on volume. That is, you get rid of the volume, which is the argument of u, and bring in the derivative of u with respect to the volume, which is minus p or p, in its favor. And to do that, you have to subtract from u the product of minus p times v. That is, you have to add pv to u. Now notice that in this case, among the arguments of u, s is not being Legendre transformed. So del 2h del s2 actually is exactly the same sign as del 2u del s2. Of course, the former is done at constant p and n, and the latter in terms of constant v and n. But that doesn't matter as far as the sign is concerned. As you will see soon, this is not quite as trivial as I've made it sound. What actually reverses sign is del 2h del p2. The variable which has been brought in this case, by doing the Legendre transformation is p, and the variable that you have gotten rid of is v. Del 2h del p2 would actually be negative of 1 over del 2u del v2. And since the latter was greater than or equal to 0, this one has to be less than or equal to 0. So this is the condition which H has to satisfy. Well, F, the Helmholtz energy, is obtained by doing a Legendre transform on the other variable. That is, you get rid of entropy, bring in the derivative, that is temperature, in its place by subtracting Ts from U. And now, it follows that del 2 of del T2 changes sign, it becomes less than or equal to 0. Del 2 of del V2 is not touched. It still stays greater than or equal to 0. And for Gibbs free energy, actually one in which both S and V are Legendre transformed away in favor of T and P, you actually get a reversal on both the derivatives compared to U. Del 2g del T2 is less than or equal to 0, and del 2g del P2 is also less than or equal to 0. So these are the conditions that follow from considerations of the Legendre transformation. The last one indicates correctly that G is a concave function of temperature and pressure. Now, of course, as we have already seen before, second partial derivatives being less than or equal to 0 does not imply concavity. What you really need in addition is this kind of condition. The stability condition would require also a result for the mixed partial derivative, and it cannot be too big. Del 2g del T2 times del 2g del P2, for example, if you are looking at G, must be greater than or equal to the result for square of del 2g del T del P. The mixed partial derivative cannot be too big, because if it is, then when you go in an intermediate direction between T and P, concavity of G would be violated. Now, it so turns out that this kind of mixed partial derivative result, while they're essential, you don't really need to talk about them if you're talking of all the thermodynamic potentials together. As we have already mentioned, the variable that is not Legendre transformed corresponds to an inequality that does not change sign. This is why del 2h del s2 or del 2f del v2 are both greater than or equal to 0. However, as I mentioned then, the proof of this is not really very straightforward, and that is what we are going to discuss now. What we are going to do is try to rewrite this del 2f del v2 in terms of derivatives involving u. Now, the first derivative of f with respect to v is of course minus p. Now, pressure can be obtained as a function of svn by taking the negative derivative of u with respect to v. That's of course something we all know. Now, if you think of p as a function of svn, then dp is of course del p del s with v and n held fixed times ds plus del p del v at s and n fixed times dv plus del p del n at s and v fixed times dn. In what is going to follow, we are going to assume that we are dealing with closed systems, so dn will be 0 throughout. So I may or may not bother writing down the n constant every time. Or may omit this third term here simply because dn is 0. Now let's try looking at the second derivative of f with respect to v minus del p del v at t comma n, but using this version for p expressed as a function of s, v and n. So del 2f del v2 at constant t and n is nothing but minus del p del v at constant t and n. But I'm going to use this expression. Of course, this term drops out because n is constant. And what I get is the following. From this term, I get del p del s at constant v comma n times del s del v at constant t comma n. Of course, the minus sign here is simply the overall minus sign here. And from this term, you just get minus del p del v at s comma n. Once again, this minus sign here is nothing but the minus sign that you have on the left hand side. Now, this del p del v at constant s comma n is actually a second derivative of u. Remember, p itself is minus del u del v at constant s comma n. So this term is actually, with the minus sign, del 2u del v2 at constant s comma n. What we will try to do is rewrite the other two terms also in a similar fashion. Notice del p del s is actually del 2u del s del v. But in our mixed partial derivative condition, you actually have the square of the mixed partial derivative. Motivated by that, or by algebraic convenience, what we do is actually we square this term, right? This is minus del p del s whole square. But of course, if you do that, you have to multiply by its reciprocal to get back just this. So you have to multiply by del s del p at constant v comma n. So you have minus del p del s whole square del s del p at constant v comma n times del p del t at constant v comma n minus this term. Now we replace these terms by their corresponding expressions in terms of u. But before we do that, this product, both of them are being carried out, both of these partial derivatives are being carried out at constant v comma n, so they behave essentially like standard derivatives. This product is del s del t at constant v comma n. Now notice what we can do with this. T is del u del s, and this is the reciprocal of del t del s at constant v comma n. So you can write this as 1 by del 2u del s2 at constant v comma n. This term, as you have already seen, is nothing but minus del 2u del v del s. You are squaring that, so the minus sign essentially goes away. There's of course this overall minus sign outside. And this term, along with the minus sign, is del 2u del v2 at constant s comma n. So what we have managed to do is rewrite our second derivative del 2f del v2 at t comma n, which, remember, our condition told us is greater than or equal to 0, essentially in this form. Now, because del 2u del s2 is already known to be greater than or equal to 0, the whole thing being greater than or equal to 0 implies that this is greater than or equal to 0. So the condition that we have on the mixed partial derivative not being too big of u is actually contained within del 2f del v2 being greater than or equal to 0. This is why we said that you do not really have to worry about the mixed partial derivative conditions. Strictly speaking, we have really turned the logic a bit on its head right now. What would actually be correct to say is that we already know that u is a convex function of its arguments. And from that, the condition on the second derivatives of u and the mixed partial derivative condition of u follows. So the correct interpretation of what we have just done would be that we have actually proven that del 2F del V2 is greater than or equal to 0 using the convexity of U. In fact, the fact that del 2H del S2 is greater than or equal to 0 can be proven along exactly similar lines. Indeed, so can the condition on the mixed partial derivatives of G. I would urge you to try your hand at proving these results. If nothing else, it would give you some good exercise in handling partial derivatives as we do in thermodynamics. But the upshot of all this can be summarized in the following. If you consider all the direct second derivatives, by which I mean non-mixed second derivatives, of all the thermodynamic potentials and consider the inequality satisfied by them, you do not have to take into account the mixed partial derivative conditions on top of that, because the conditions that you have already stated subsumes those. Now, let us take a look at some physical consequences of stability. We have already seen some of them down the line, but let's make this formal now. The one condition that we have already seen, concavity of S with respect to its arguments, implies when delta U is very small, the fact that del 2S del U2 at V, N is less than or equal to 0. But del S del U at V, N is 1 over T. So this is really del U of 1 over T at constant V, N, which is nothing but minus 1 by T square del T del U at constant V, N. But remember, del U del T at constant V, N is nothing but d cross Q dt at constant V, N, because when you are holding V constant, the PdV term, the work term, is 0. So change in internal energy is entirely due to heat flow. And this is nothing but the heat capacity at constant volume. If you write this in terms of the molar heat capacity small cv, this is N times small cv. So what this expression on the left hand side of the inequality here is simply minus 1 over Nt square cv, and this has to be less than or equal to 0. And since both N and T square are definitely positive, this tells us the cv must be greater than or equal to 0 if your system is to be a stable one. So that's one very important condition. It's a physically significant result that heat capacity at constant volume can never be negative, something which follows from the stability considerations. For the next one, we will start with del 2F del V2 at constant T, N. This is greater than or equal to 0. Remember, this is nothing, as we have already seen, but the condition on mixed partial derivatives for U. But let's directly work with del 2F del V2 because that's the most convenient thing to do here. Now, F has a first derivative with respect to V, which is actually P with a minus sign. So this thing is nothing but minus del P del V at constant T, N. And if you supply an additional V with this becomes reciprocal of the isothermal compressibility. The isothermal compressibility, something which describes how fast or how efficiently you can compress a system when you change the pressure, essentially is 1 by V del P at constant T, N. But there's a minus sign simply because volume typically decreases with pressure. In fact, what we will see right now is that the stability condition demands that volume has to decrease with pressure at constant T, N. As a result, this minus sign ensures that kappa T is positive. And that is exactly what the stability condition is telling us, because this expression is nothing but 1 over V times kappa T, and stability insists that this is greater than or equal to 0. So kappa T has to be, the isothermal compressibility has to be greater than or equal to 0 in a stable system. Now, this is not the only set of physical conditions that you can figure out from here. There are more results that can follow. Now, in order to see some of them, let's first recall that the heat capacity at constant pressure can be related to the heat capacity at constant volume by a rather well-known result. Now, I usually never memorize that result, I work it out. So let's work it out again. The overall heat capacity at constant pressure, which is capital N times the molar heat capacity, N small Cp, is nothing but T del S del T at constant P, N. And because we can write S as a function of temperature and volume as well, and carry out this partial derivative, this del S del T at constant P, N becomes del S del T at constant V, N plus del S del V at constant T, N times del V del T at constant P, N. So this term T del S del T at constant V, N is nothing but the heat capacity at constant volume, or N times the molar heat capacity at constant volume, N times Cv. Now what you are multiplying this by is T del S del V at constant T, N times del V del T at constant P, N. Del P del T at constant V, N is what del S del V at constant T, N equal to. This is one of the Maxwell relations that we had already talked about before. And then what we can do is rewrite this slightly. This del P del T at constant V, N can be written down in terms of del P del V divided by del T del V with a minus sign. That is, you can write del P del T at constant V, N as minus del P del V at constant T, N by del T del V at constant P, N. And now you can rewrite both of these terms. The top, once it's applied with a V, and of course the bottom also with a V, the top here essentially becomes reciprocal of kappa T with the minus sign. And the bottom term here is actually how fast volume expands with temperature, and is related to the alpha. Of course, you already also have a del V del T at P, N. Putting all these together, you get the result that NCP is NCV plus TV alpha square by KT. So, Cp minus Cv, the difference, becomes T times small v. Small v, of course, is the molar volume, capital V over N, alpha square by kappa T. So, the all important result that we are looking for here is Cp is actually greater than or equal to Cv always. And Cv, the latter, is also, of course, according to stability greater than or equal to 0. We can actually make a similar statement about the adiabatic compressibility, kappa S. Kappa S, like kappa T, is described in terms of minus 1 over V del P, but this time at constant S and N. And by expressing V as a function of temperature and pressure, we can rewrite this as follows. The del V del P at constant S, N can be written down as del V del P at constant T, N plus del V del T at constant P, N times del T del P at constant S, N. The first term here is, of course, the isothermal compressibility. In addition to that, you have this term. And by squaring this term and multiplying by its reciprocal, we actually end up with del T del S at constant P, N. And del T del S at constant P, N is easily seen once you supply it with a T below to be N times small Cp. So kappa S works out to kappa T minus TV alpha square by Cp, actually small v alpha square by Cp. That's the molar volume. Now, you can easily see from this that kappa S divided by kappa T is 1 minus TV alpha square, small v alpha square, of course, by Cp kappa T. Now, T small v alpha square by kappa T is nothing but Cp minus Cv. plug that in, cancel out the 1 and the Cp by Cp from here, you get Cv by Cp as the ratio. So kappa S by kappa D ratio is actually the same as the Cv by Cp ratio. So what you end up with is kappa T is greater than or equal to kappa S simply because Cp is bigger than or equal to Cv, as we have already seen, and kappa S has to be greater than or equal to 0. Simply because this side is of course positive, Cp, Cv both being positive, and so must this side be. Kappa T we have already seen is positive, so kappa S also has to be positive. So kappa S, although smaller than kappa T, is also guaranteed to be positive by stability. So physically what this tells us is that if you add heat either at constant pressure or at constant volume to a region, it raises the temperature of the system. And the temperature rises more at constant volume than at constant pressure. Similarly, it says that if you decrease the volume either isothermally or adiabatically, this will lead to an increase in pressure. More so if you were to do it isothermally than adiabatically. Now, this we could have argued without the mathematics on the basis of physics as well. Suppose, to the contrary, Cv were negative. Then what would happen is that if I were to locally heat up a region, its temperature would go down compared to the rest of the system. Then heat would keep on flowing in to that part because it's now at a lower temperature compared to the surroundings. And of course, that would mean the system would go down further in temperature with heat keeping on flowing in, and the whole thing will become unstable. Similarly, if the isothermal compressibility had been negative, then if due to some fluctuation pressure changed in a small region, what would happen is that if the pressure dropped there, its volume would try to grow, pushing the rest of the system back. And that would make the pressure fall further. And as a result, the system would again become unstable. Now, what we are seeing here essentially is Le Chatelier's principle in action. We will have more to say about Le Chatelier's principle later, but what this principle says is any inhomogeneity that develops in a system or part of a system should induce a process that tends to eradicate this inhomogeneity. And that's exactly what stability says has to happen. Now we will have a lot more to say about Le Chatelier's principle and a related, not so well known principle called the Le Chatelier-Brown principle in the next lecture. But today, let me finish by taking a look at whether a rather well-known system actually obeys these criterion that we have laid down for stability. In particular, what I'm going to do is take a look at the van der Waals gas, which obeys the well-known equation P plus n square A by V square times V minus NB is nRT, and try to see whether the isothermal compressibility for this van der Waals gas actually is always greater than or equal to 0. For that, we simply need to calculate del V del P at constant temperature and number of moles. So we just differentiate both sides with respect to pressure. This gives me 1. This of course gives me minus twice n square A by V cube times del V del P at constant T comma n times V minus NB. I'm just using the formula for differentiating a product here, plus P plus n square A by V square. This gives me del V del P at constant T comma n. This of course gives me 0 because n is held constant. The right hand side, because T and n are both held constant, gives me 0. So once I collect all the terms with del V del P at constant T comma n, of course these two terms as well as this term minus twice n square A by V cube into V minus NB, this is what the expression becomes equal to. V minus NB times 1 plus this whole thing equals 0. And this, of course, can be simplified a bit, because when you multiply this, you get P minus n square A by V square plus this term with an AB in it. Now, just by rewriting this expression, isothermal compressibility, which is minus 1 over V del P at constant T comma n, works out with this 1 minus NB by V by P plus twice n cube AB by V cube minus n square A by V square. Now, one thing that you can always check is the simple case. If A and B were both 0, this van der Waals gas would reduce to an ideal gas, and we know that the isothermal compressibility for an ideal gas is simply 1 over its pressure. This expression, in the limit where A and B both go to 0, does reduce to 1 over P, which should give us some confidence that we had done the calculation right. But what is important is, unlike the ideal gas, where kappa T is 1 over P and hence is always greater than or equal to 0, here, if you look at this expression, it's easy to see that for small enough molar volumes, that is for dense enough systems, this term would become negative. As a result, there is no guarantee that this is necessarily positive. Now, what does this indicate? It indicates that the van der Waals equation does not necessarily describe a stable system. We will see this in more detail when we talk about phase transitions in the van der Waals system. But this is a clear-cut indicator that there are regions in the isotherms describing a van der Waals system where volume actually goes up when pressure increases, rendering the system unstable and causing inhomogeneities to occur naturally in the system. This inhomogeneity actually gives rise to the liquid-gas phase transition in a van der Waals system. We will see this in much more detail in a later lecture. I would have loved to actually give you the complete proof for the Chatelier-Brown principle today in this lecture. However, that's a bit lengthy, so I will leave this for the next part of the lecture. Let's call it a day today.